In this assessment, we observe a fragmentation pattern that gives us this benzyl carbocation and asks us why this benzyl carbocation might be the base peak in the mass spectrum, meaning the peak that is of greatest intensity. Now, it's not always true that what happens in the mass spectrometer will resemble the reactivity patterns that we learn in solution phase. But in this case, it's happening. In this case, the fact that this is the base peak can be explained using our understanding of carbocation stability. And so if we look at this benzyl carbocation, we note that we can draw several resonance structures. I'll just draw a couple where we can delocalize this positive charge. We could draw one more that I'll draw. There are a couple others, but we can continue to delocalize that carbocation around the benzene ring. As a result, that's a stable carbocation, and we would expect it to persist longer in the mass spectrometer and be more likely to be detected. That's the reason that this is the base peak in the mass spectrum. Before I go, in addition to stabilizing this carbocation through resonance, it turns out that this benzyl carbocation can rearrange to another more stable molecule. That molecule is what we refer to as the tropylium ion. So it's a 7-membered ring that looks like this. We're going to find out later on why this is such a stable molecule, but this also is going to have the same molecular mass or the same atomic mass as the benzyl carbocation, the same 91 mass to charge ratio. This is another reason that the peak corresponding to 91 mass to charge will show up. Formation of this tropylium ion. Kind of an advanced concept, but just to make sure that this video is correct, we'll include that as part of the analysis.